Hello everyone, you are welcome. In this video, we will continue our discussion on magnetism. Our focus will be on magnetic fields, magnetic effect of currents, Fleming's left-hand rule, and the Motor effect. Magnetic field. The space surrounding a magnet where it produces a magnetic force is called a magnetic field. A magnetic material, when placed in this field, will experience a force. It doesn't have to be close to the magnet to experience the force. The magnetic field is represented by lines referred to as lines of force or field lines. The magnetic field has a direction. The direction is shown on the field lines. A compass is usually used to find the direction of the field. The compass has a needle which is magnetic, which turns freely on its spindle. When placed in a magnetic field, the north pole of the compass needle will consistently point away from the north pole of the magnet and point towards the south. By moving it from one point to another in the field and indicating the positions with dots, a line can be traced to get the line of force. The direction of a magnetic field line is said to be the direction in which the north end of a compass needle would point. And we see this shown in the image. From the diagram, the field lines run from the north pole to the south pole of the magnet. The closer the field lines, the stronger the field. The strength of the magnet is therefore concentrated at the ends of the magnet. If two magnets are placed near each other with unlike poles facing each other, their magnetic fields combine to form a single field. When two like poles are brought together, they repel each other. The magnetic field lines do not come together. At the neutral point, the field from one magnet exactly cancels the field from the other, so no magnetic force is felt at that point. There are no lines of force. Hope you're enjoying the video so far. Please don't forget to subscribe, comment, leave a like. Magnetic effect of a current. When current is passed through a conductor or wire, a weak magnetic field is produced around the conductor. We'll consider two instances, that of a straight conductor and a coil. First, let's consider the straight conductor. The magnetic field has the following features. The magnetic field lines are circular. The field is stronger close to the wire. Increasing current increases the strength of the field. Given that the magnetic field lines are circular, how do you determine the direction of the field? We use the right-hand grip rule. The rule states, grip the wire with your right hand so that the thumb points in the direction of the current. Your fingers will point in the direction of the field. So please take note that it's the right hand that is used, not the left hand. Using the left hand will give you an error in the direction of the field. Change the direction of the current will change the direction of the magnetic field. So in the image, we see the thumb pointing upwards in the direction of the current. The fingers curl around the conductor, pointing towards the person and indicating the direction of the field. Solenoid or coil. When current is passed through a solenoid, the direction of the field produced can be found using the direction of the current. If the current direction is clockwise when viewed from one end of the solenoid, then that end will be the south and the other end will be the north. Field lines will then move from the north pole to the south pole. You can also use a right-hand grip rule to find the direction of the field. The right-hand grip rule as applied to solenoid or coil states that grip the solenoid with your right hand such that your fingers point in the direction of the current. Your thumb will show the direction of the field. Where the thumb will point will be the North Pole. Changing the direction of the current will change the direction of the magnetic field produced. And we see that depicted. The field produced is similar to that of a bar magnet. There are magnetic poles at the end of the solenoid or coil. Increasing the current increases the strength of the field. Increasing the number of turns will equally increase the strength of the field. The motor effect. We've seen thus far that when current is passed through a conductor, a magnetic field is set up around it. What if that current carrying conductor is placed in a different magnetic field? A wire carrying current, when put in a magnetic field, experiences a force. If the wire can move, it does so. In the image, magnetic field lines are moving from the North Pole to the South Pole. If current starts flowing through the conductor placed in the field, a force will be produced on the conductor. The force is produced as a result of the interaction between the field due to the magnet and the field created around the conductor when current starts flowing through the conductor. The interaction between the two fields produces a force which acts on the conductor. But what is the direction of this force that is produced? To determine the direction of the force produced, we use Fleming's left-hand rule. The rule states, hold the thumb and the first two fingers of the left hand at right angles to each other, with the first finger pointing in the direction of the field and the second finger in the direction of the current. The thumb will then point in the direction of the thrust or force. If the wire is not at right angle to the field, the force will be smaller, and the force will be zero if the wire is parallel to the field. Remember, if you use the right hand, the direction of the force will be wrong. So then how do we use the rule in the diagram we see? The left hand has to be turned such that the direction of the fingers would follow what the law says. So in the diagram, even though I'm unable to show the hand in 3D, I've managed to position in a way for you to appreciate it. A downward force is produced. Please take note that changing the direction of the current will change the direction of the force. Changing the direction of the magnetic field will change the direction of the force as well. If both the current and the field change direction, then it will be like one effect cancels the other out, and so the direction of the force will remain unchanged. So the force changes direction only when one of them changes. Either the direction of the field changes or the direction of the current changes. This whole concept of a force produced on a conductor carrying current placed in a magnetic field is the motor effect, because the same principle is used in the operation of motors. We are going to talk more about a simple DC motor in the next video. We'll move ahead to look at generators and other applications. Thank you very much for watching. Please don't forget to subscribe, leave a like, or comment in the section below. See you in the next one.